Alright guys, welcome to today's lesson in statics. Today we're covering problem 52 from chapter 3. So number 52 is a continuation of problem 51 we did in an earlier video. And 52 says, for the dab of problem 351, determine the largest allowable distance x when the tension line ABAD is 60 pounds. So in this problem they're giving us the tension of the line ABAD, and they want us to find the value of x right here on the x-axis from, it appears to be from point C to D. So I've gone ahead and laid out a few of the things we know from problem 51. They told us in problem 51 the moment about z-axis, 279 foot-pounds. They've given us the tension in this problem, that's still different, 60 pounds of force. Now they want the distance x, the maximum allowable distance. So recall from problem 51, we've determined that the moment about the z-axis is simply k hat unit vector dotted with the moment about the origin, moment about C, which expands into the position vector going from RC to point A across the resultant force acting at point A. So remember we have point C, our origin, a moment about that, due to the force at point A, we do the position vector RC to A, cross the sum of the forces at point A. And we expand this further into our determinant of our matrix, where we have the 0, 0, I hat and j hat, and then k hat value. That's when we're dotting or doing our mixed product, the k hat here. We have our position vector RCA. It's one of these components. It's x component, y component, and z component, the components of this vector. And then we have our x, y, and z components of our reaction force, our resultant force at point A. So remember drawing a free body diagram from the previous problem, we have point A, we have apparently two tension forces, tension AB acting down the negative j hat, negative y axis direction, and we have our tension in going to point D, tension from A to D, that vector as well. So determining or to determine this resultant, we need to first determine tension AB and tension AD. We can look at the tension value given, determine that it's 60 foot-pounds acting down in the negative y direction, negative j direction for tension AB. So I can simply write tension in the line AB is equal to the tension in the whole line ABAD multiplied by the negative j hat direction. And this time they give us this tension force. So this tells us the tension value from A to B is simply negative 60 pounds of force in the j hat direction. So we already have our tension in the lines A to B. Now we need to determine what the tension vector in AD is, and that'll help us determine what the value of x maximum should be. So tension AD, we know it's going to be equal to the tension value they give us, tension AB, AD, we already have that, over the distance from A to D, and that's multiplied by the position vector going from A to D. So first we'll determine what this position vector is right here, R A to D. So if I were to write it out, I would look at the diagram and say, okay, going from point A, davit, to point D, down where it's tied into, it appears that we're going, again, from problem 51, we're going out x dimension. Our dimension is on the I hat is going to be the x value. So the x value in the I hat direction, unknown, trying to solve for this problem. We're going down 7.75 feet, so minus 7.75 in the j hat direction. And we're coming out on the z-axis, coming out of the page by 3 feet. So plus, actually we're going into the page, I apologize, going from A to D, not D to A, going from A to D, going out, we're going into the page by 3 feet, so it would be minus 3 in the k hat direction. Now we can use this to determine an equation for our distance. The x will be factored in there, that's fine. So our distance formula tells us it is simply the square root of each one of these components squared and added together. So it will be square root of x squared plus, in parentheses, negative 7.75 squared plus, in parentheses, negative 3 squared. So we're going to have our square root of x squared And then we're going to have to combine these two terms. So in parentheses, negative 7.75 squared plus, in parentheses, negative 3 squared. So this gives a value of 69. We'll round this up to 69.1. Now we can write out our tension vector from A to D as follows. We know this is 60 pounds. We know that we have equations now for our position vector and for our distance value. So we have tension A to D is equal to tension in the line ABAD, which we know is 60 pounds. We have our formula down here, our equation for our distance is square root of x squared plus 69.1. We're actually going to go ahead and we'll actually go ahead and write this one time, and remember it's distributed out. So we have underneath the square root of x squared plus 69.1, and now we're going to have these values distributed out to each one of these components. So we'll have x in the I hat direction minus 7.75 in the j hat minus 3 in the k hat. Good to know. Now we're going back up here. We have our tension AD. We have our tension AB. We can find the resultant. Recall the resultant at point A is equal to, we have two tension forces going down, tension AB pulling down with the davit, and one tension force A to D. So we'd have two tension from A to B, plus one tension value back for the vector going from A to D. So we substitute this in, we'd have 2 times negative 60 j hat plus our tension value here for A to D. We're going to write this out now. It's going to be 60 times x. Take 60 times x I hat over square root of x squared plus 69.1. I should write this I hat separately off to the side. Minus, we're going to multiply 60 times negative 7.75. Okay, let our calculator catch up. Okay, so we're going to calculator catch up. So we're going to multiply 7.75 times 60. Okay, so we have 60 times 7.75. And then we're adding in, don't forget, this twice this AB vector, which is negative 60. So we have negative 465. Okay, so we'd have 60 times negative 7.75, which would be minus 465 over the square root of the same value, x squared plus 69.1 j hat. Although we actually have another j hat value, don't forget, we have our 2 times tension AB. So this would be minus 120 separate value. This would all be in the j hat direction, this component for resultant in A. And then finally, we'd have this 60 value times negative 3, so it would be minus 180 over x squared plus 69.1. Now, when we go back to our determinant, not all these values we use because we're only dealing with a k hat variable for the mixed triple product. So now at this point, we can go back and determine what our the value is for x by simply saying moment about z is equal to k hat dotted with moment about the origin at point C. So we'd have this, we'd just simply set up this determinant for this matrix. And don't forget we have to copy that on these two rows as well. So we'd have 0 for our first value, our I component going from C to A. I don't believe we actually have the determinant yet, so let's go ahead and determine real quickly what the vector is. The same from problem 3.51 and 3.26. So let's determine what is the vector going from C to A. So going in, looking at the figure from C to point A, we'd have no movement in the x-axis direction. It's in the y-z plane. This would be 0 I hat going from C to A, going from point C to point A. In the y direction, we're going up 7.75 feet. So plus 7.75 feet. We won't include units until our final answer though, j hat. And then we're coming out of the page now with a dimension of 3 feet. So it'll be plus 3 k hat. Good. So we have our unit vector k hat. For a moment about the z-axis is only k, so it'll be 0. Our position vector r from C to A, the origin to the point where the force being applied is also 0. Now this component, we'll have to write out each one of these values. This will be 60x over the square root of x squared plus 69.1. Now we have no value here. Our y component for our CA position vector is 7.75. Here is our j component. So we have 465 divided by this equation, 7x squared plus 69.1 minus 120. And finally we have our k hat component here. I can see, put it in frame. Okay. Then we have our position vector here telling us positive 3. We finally have our z component, our k hat value of negative 180 for the resultant at point A of over x squared plus 69.1. We also need to copy down the first two rows again. So we'd have 0, 0, 60x over x squared plus 69.1. We have a 0 value again, 7.75 for position. And our 465 over x squared plus 69.1 minus 120. Good. Now when we evaluate this, we have a good number of zeros, so most of these terms will end up being 0. So when we work this out, one about z is equal to going down to the right we're going to add, up and to the right we're going to subtract. So it would be plus a 0, 0 here, and finally k hat another 0 right here. Now we're going to subtract, and we do get a value here. So we have 7.75 times this part 60x over the square root of x squared plus 69.1 in the k hat direction. Now we're subtracting again. We have a 0 here. And subtracting again, finally we have 0 here. So recall, our moment of z was equivalent to 279 foot-pounds from problem 351. Okay, so now to finish this problem off, we require a little bit of algebra. We know this moment force, they told us, is 279 in problem 351, which is where we're sourcing this problem from. That's equal to, we multiply these two values together, 7.75 times 60. I believe we've already done that before. I believe we got 465. We can always double check. 60. Yeah, we already have it on the screen, actually. 60 times 7.75 we know is 465 right here. So we have minus 465 x divided by x squared, square root of x squared, plus 69.1. Now do a little algebra, multiply both sides by the square root. Square root of x squared plus 69.1. Multiply this side as well. This is going to be multiplied by the square root of x squared plus 69.1. This will cancel here. Okay, we can then divide both sides by 279. Divided by 279. So now we rewrite this. We get over here, we get a value of square root of x squared plus 69.1 is equal to negative 465 x divided by 279. So we're going to square both sides here. That'll cancel the square root. This will cancel, so we get x squared plus 69.1 is equal to this term squared. So we're going to square in parentheses I'm going to square in parentheses negative 465 divided by 279 I'm going to square that, and this will give us a value, as soon as the calculator catches up, give us a value equal to 2.7 repeating, so 2.78, and x squared is simply just x squared will give us just x squared. So we can go ahead and subtract minus 1x squared over here, implied 1, always remember, minus 1 minus an x squared over here. So this would give us minus 1, this would just give us a 1.78 x squared value equal to 69.1. We can divide both sides by 1.78. Okay. That will tell us x squared is equal to, let me do 69.1 divided by 1.78. Gives us a value of 38.82. This is x squared. Don't forget, take the square root of this side. It'll cancel out. Square root of this number. So we're going to square root our answer. So we square root our answer. And this will give us a value of x being equal to 6.23 feet. So our final answer is x equal to 6.23 feet. Alright guys, thanks for joining me in another Simple STEM Solution video. Be sure to like and subscribe. Also, if you'd like to support this channel or have particular questions you want answered, be sure to check out my Patreon community via the link in the description below.